There's one element that pretty much builds everything. The world around us and, yeah, even us. It's like the ultimate architect of life. And today, we're diving deep into the secrets of carbon. So, what's the big deal with carbon, right? I mean, out of all the elements in the entire universe, how did this one single element become the absolute champion of construction, the architect of all biology, the very foundation of organic chemistry? Well, that's the big question we're going to tackle. I mean, think about it. Carbon's influence is, well, it's everywhere. It's in the plastic of the phone or computer you're watching this on right now. It's in the fuel that powers our cars and homes. And maybe most mind-blowing of all, it's the central scaffold of the DNA that makes you, well, you. It's no exaggeration to say it's the ultimate builder. So the secret to carbon's success, it really comes down to one incredible ability. It just loves to link up with itself. It forms these super long, super stable chains that act like a molecular backbone. You can think of it like a sturdy frame where all the other complicated bits and pieces of a molecule can just snap right into place. Okay, so to really get a handle on carbon's building skills, we gotta zoom in on its favorite tool, the carbon-carbon bond. Seriously, this one connection is what makes the entire world of organic chemistry even possible. So what is it exactly? Well, it's something called a covalent bond. The easiest way to picture it is just two atoms kind of holding hands. See, each carbon atom shares one of its electrons with the other one, and that shared pair creates this really powerful, really stable link between them. But here's the cool part. Carbon doesn't just hold hands in one way. A single bond, where they're sharing just one pair of electrons, that's kind of like a flexible handshake, right? It lets the atoms twist and rotate around. But they can also form double or even triple bonds, sharing two or three pairs of electrons. And that's way more like a rigid, locked-in grip. No rotating there. And you can actually see this in the numbers. It's fascinating. A single bond, like in ethane, is about 154 picometers long. Okay, but now look what happens when you add a second bond in ethylene. It shrinks down to 134. And a triple bond, like in acetylene, it pulls them even tighter, all the way down to just 120 picometers. It's amazing. More shared electrons literally pull the atoms closer together, and that forges a much, much stronger connection. So this ability to bond in different ways, that's just the beginning. Carbon has what I like to call two architectural superpowers. And these are what let it build the millions and millions of different compounds we see all around us. All right, superpower number one, catenation. Yeah, it's a fancy word, but the idea is super simple. Carbon is just uniquely good at bonding to itself over and over again to form these long, incredibly stable chains. You might be thinking, hey, what about silicon? It's right next to carbon on the periodic table. And yeah, silicon tries, but its bonds are just weaker, more reactive. And that right there is why carbon, and not silicon, is the backbone of life. And then we have superpower number two, tetravalence. This just means that every single carbon atom can form 4 bonds. 4. Think of it like the perfect 3D connector piece, like a Lego with 4 connection points. This is huge because it means carbon doesn't just build in a straight line. It can branch out in all directions, creating these wonderfully complex 3-dimensional structures. Okay, let's put these superpowers into action and actually watch a molecule grow. The most basic thing you can build is a simple straight chain, just like this one here. This is the foundation for a ton of everyday molecules, like, say, the propane you use in a gas grill. But remember tetravalence, that second superpower? Thanks to that, we don't have to stick to boring straight lines. Carbon can create branches that shoot off the main chain. And this branching ability, this is the key. It's what allows for the huge, huge diversity of molecular shapes we see all throughout nature. And get this, the chains don't even have to be open-ended. They can actually loop back on themselves, forming these incredibly stable rings. And these ring structures, they are absolutely fundamental. We're talking critical molecules like sugars, steroids, and, yep, even the building blocks of our own DNA. All right, so now that we've got the basics down, let's have a little fun. Let's look at how chemists have pushed these carbon-carbon bonds to their absolute breaking point limits. Get ready for some real record breakers. First up, the longest carbon-carbon single bond ever measured. So in this one specific, incredibly crowded molecule, chemists found the bond in the middle was stretched out to a whopping 167 picometers. That is way, way longer than average. It's literally being forced apart by all its bulky neighbors. And because it's stretched so thin, that bond is also ridiculously weak. It only takes a tiny amount of energy to break it. We're talking about 8 kilocalories per mole. Now, to put that into perspective, a typical carbon-carbon bond needs around 90 units to break. So this one, it's so fragile, it practically falls apart if you just look at it wrong. Okay, now let's flip to the complete opposite end of the spectrum. Check out the triple bond in acetylene. To break this thing, you need a massive 230 units of energy. That makes it one of the strongest, most stable chemical bonds in all of organic chemistry. It's an absolute beast. So this is all really fascinating chemistry, for sure. But why does any of it matter to you in your day-to-day life? Well, it matters because these molecular blueprints, they are the key to building our entire modern world. So here's the crucial point. Our entire ability to create new stuff, I'm talking everything from life-saving drugs to the plastics we use every day, it all hinges on our ability to make and break these carbon-carbon bonds with incredible precision. I mean, just look at the results. Super complex molecules like cortisone and morphine, they rely on very specific 3D carbon skeletons. The plastics all over our homes, the fuels in our cars, even the proteins and fats inside our own bodies, they are all built on these exact same principles. This is why getting a handle on carbon chemistry is just so important. So, carbon basically gave us the blueprint for life itself. And over the last century or so, we've learned how to use that same blueprint to build the modern world. The big question now is, as our understanding of these bonds gets even deeper, what on earth are we going to build with them next?